Example, we are going to analyze Colonel Steps. One of his experiments he did while working for the Air Force to determine how many G's aircraft pilots could withstand in aircraft. His example looks something like this. He was accelerated up to, in his rocket-powered sled, to 632 miles per hour. And he was brought to rest or decelerated to 0 miles per hour in a total time of 1.4 seconds, which is not much. So those are very sharp deceleration rate there. And so in this problem we want to find three things. We want to find the acceleration rate that he underwent, how far he traveled, x, while he was decelerating, and c, how many g's he withstood. And g is a comparison made to the gravitational acceleration. So when we want to determine how many times the acceleration due to gravity he underwent during this deceleration. The first thing I notice here is that we have units of seconds and miles per hour. And so we have two different units for time, and we usually don't want to do that. We want to have the same unit for time. In addition, this is miles, so I want to get everything in meters per second, like we've done in previous problems. So I'm going to do a little conversion factor here, a couple conversion factors. So to get rid of the hours, I know that 1 hour is 3,600 seconds. And I know that 1 mile is 1,609 meters. That's a meter there. So the hour will cancel that. The miles will cancel there. And I'll be left with a meter per second. And this comes out to 282.5 meters per second. So I'll do that little conversion right here in the beginning so we can take care of that. Equation-wise, I have my three equations, my three kinematic equations. And again, we write these here just as for organization. You don't have to memorize these, but it's nice to use this as our work area. V equals V0 plus AT, and V squared is equal to V0 squared plus 2AX minus X0. Then for variables, I have X0, X, V0, V, acceleration, and time. And again, this is probably the most important part. If you can get these variables here, then you are just, you have to do some math to get the answers. So I'm going to, again, put my origin or my ruler right here on the ground, and this is going to be the positive direction, the positive x direction, okay? And therefore the origins right here is 0. So my initial displacement, where I begin, is 0. How far I travel, I do not know. That's what I want to find over here. My initial velocity we converted already, so we're at 282.5 meters per second. I come to a stop, so that's 0 meters per second. My acceleration rate I do not know, although I do know it's going to be negative meters per second squared. Negative because I know my initial velocity here points to the right, or in the positive direction, because velocity is a vector. And so to slow down, my acceleration's got to point the opposite direction to counteract the velocity. If acceleration pointed in the same direction, it would speed up the car. But we're slowing down, so the acceleration vector must point in the opposite direction, or in the negative direction. So I know it's going to be a negative number. And the time I have down here is 1.4 seconds, so I know that. So looking at the variables here, x I do not know, acceleration I do not know. I know initial displacement, velocity, and time. Acceleration, again, I don't know. And acceleration and x I don't know. So this lets me see at a glance what variables and which equations I do not know. It helps me figure out which one to use to solve. So part A, solve. I want to find the acceleration rate. So this first equation does have acceleration, except it also has unknown of x. So two variables, two unknowns in one equation is not good. Now I also see the same two here, so I could actually do substitution in algebra to determine that. However, I can just use this one right here because it has only one unknown. So v is equal to v0 plus a t. So if I solve algebraically, a is equal to v minus v0 over time, which is 0 minus the 282.5, my initial velocity, 1.4 seconds, which gives me a number of negative 201.8 meters per second squared. And you can see I got the negative sign here, which I thought I had. So the moral of the story is that if I have the correct values in my equations, I will actually get the negatives for my quantities if it is negative, and indeed it's negative. And again, what does the meters per second squared mean? It means I, in this case, lose, because it's negative, 201.8 meters per second every 1 second. I lose 201 meters per second every 1 second. So that's about right, because it's going 282, so 1.4 seconds. So that seems like it's in the ballpark. I would lose about 200 meters per second. Part B, the time, or excuse me, the distance, how far do I travel? So now I know the acceleration rate, and right here in this equation I could actually solve for x. I have everything I need. I could also solve for here, but I'll just use this one since I have it right here. X is equal to x0 plus v0t plus 1/2 at squared. This is 0. So I get 282.5 times 1.4 plus 1/2 negative 201.8 times 1.4 squared. That's a common mistake to get the square. And I get an answer of 197.8 meters. It's about 200 meters, which is a pretty far distance for stopping. And but considering that he's going 282 meters per second and stops in 200 meters, it's actually pretty amazing that he can come to stop in such a short distance. Finally, how many G's is this? So I'll do part C up here. Remember that the G we use for the kinematics problems where we drop something is negative 9.8 meters per second squared. How many G's is this? And when we compare to G's, we actually get rid of the negative, because this is for those vertical polygons we're actually solving for something. So we're just going to use the 9.8 as our comparison. So for part C, negative 201.8 meters per second squared. So 1G is 9.8 meters per second squared. That's what 1G is. That's a G. So the meters per second cancel. And this comes out to a value of about 20.17 Gs. 20.17 Gs. So let's think about that. 20.17 Gs. That is 20 times the acceleration rate due to gravity. If you were to drop something on the Earth, baseball or something like that, the acceleration rate is 9.8. This is 20 times that. So you can imagine the deceleration rate that Colonel Stepp felt while he was going from 282 to 0. He felt 20 times as heavier than he would just sitting on the ground, and over that 1.4 seconds. So in this problem, the kinematic model problem for Colonel Stepp, we follow the same guidelines: list equations, variables, and solve. A couple key points: if we have mixed units, we have to make sure we convert the mixed units for instance, hours and seconds to the correct ones. Pay attention to the directions on vectors and see if they make sense. Here we got a negative 201, which we thought, because we're slowing down. If I got a positive value, that wouldn't make sense because that would mean that it would speed the object up when we were slowing down. And we talked about what a g was. It's basically a comparison to the acceleration due to gravity. So that'll wrap up our third example on the kinematics model.